Now let's take a look at the multi-input adders. Suppose we want to add k n-bit words. For example, 4-bit. We have 4 bits here. We want to add them all. So this is assume that this is an unsigned number. If we add them up, those two, we will get the 1000. If we add them up again, 10101. If we add that gives us 10111, right? As you can see, this is just a straightforward implementation of addition. We will follow this logic and to constitute adder like the following. With the sum is like this. The solution for this kind of addition is we can add a 2-input adder. This is carry ripple CPA, carry propagation adder. We add 4 bits and get the output. An additional 4 bits gets the output, and like this. So we add 2 at each time at a time, so we can get the final result. But this way is very large, constitute a large area, and also very slow, because we need to go through the carry propagation of all 3 adders, right? Each adder require carry propagation from the LSB to MSB. So in case of adding large number of words, n-bit words, we use carry save adder. This is the structure of the carry save addition. So carry save addition, we use the full adder structure. As you can see, the full adder, it gets the 3-bit and give out the 2-bit. So we compress the 3-bit information onto the 2-bit information, right? So full adder sums 3-bit and produce 2 outputs. So if we put those in parallel like this, and we can reduce the number of the number of the partial addition, kind of we can reduce the number of what is it called? We number itself. I mean, first we needed to add four numbers, but we can reduce that to smaller one. So if you use this kind of a carry save addition, you can add three number of addition can be reduced down to 2 number of additions. This is more detail. So we need 3 numbers to add. We go through the carry save adder. Carry save adder gave us the sum and carry out. So here in this case, if we add those 3, sum and carry will be generated. The carry has the 1-bit higher bit position. Now the remaining 0000010 will be added through the additional carry save adder. So this the previous carry and sum just shown in here, and additional number z, the input, we get this from input. So if we add them all, then we will get the final carry and sum here, right? The final carry and sum will be like this. Then finally we get only 2 numbers to add. So at the final stage we use carry propagation adder here. Then we complete the calculation. In this formation, only carry propagation happens in the last stage. The previous stage, it goes through the half adder cell, right? It significantly reduced the propagation delay through this carry save addition. The final number will be the sum of those two, 10111. This kind of a carry save as a structure is widely used for multiplication. For example, if we want to multiply 12 by 5, the 12 is represented in binary 1100 and 5 represented in binary 0101. To do the multiplication, each bit starting from 1 multiply. So we generate the one partial product. This is partial product. And then next bit we multiply again. So additional partial product is generated. And then we generate the partial product for the other next bit. 1100 is another partial product. Finally, the next partial product is 0000. Now, to complete the multiplication, we have to add all those 4 partial products. In this kind of addition, better to use the CSA structure, carry save adder structure. The final addition value will be 60. So multiplication can be easily done by generating partial product, right? Generate partial product. Second, and add them up, right? This is a 2-step to calculate the multiplication. As you can see, for m by n bit multiplication, final number is m plus n bit output product. You have to remember this number, right? If you multiply m by n bit, then you get the m plus n bit. What if you add m plus n bit addition, that give us m plus 1 number bits for addition. If you want to avoid the overflow condition, you have to prepare m plus 1 bit for addition, right? Because the 2 maximum number will have a bigger number than the input bit allowed, right? So this is similar for the addition and also the multiplication. So multiplication require more bits at the output. In general form, so multiplicand, the y can be represented m bit, and multiplier x is represented n bit. The final product, this is just mathematical representation of those. Since this is the binary representation, we use that the weighting factor, that is 2 because of the binary. This is y and this is x, right? So multiply y by x will be like this. This is kind of a partial product generated, right? And we have to add them all. Dot diagram is an easy way to visualize the partial product. So each partial product will generate this is single bit location. This is the one partial product, right? Generated from the multiplier x, right? So this is the y is. So each partial product. This is another partial product from the multiplier x bits, right? So on the array structure, how we generate the partial product, we can simply have the AND operator will give us to generate the partial product, right? And then this partial product is added through the half adder, full adder. It had 1, 2, 3 bit addition, right? So this rectangular box represent the partial product generation and carry save adder structure. Full adder is inside. So in this, by having this, we can generate the partial product and add through this array structure. At the final stage, you know, this is the carry save adder, right? Carry propagation adder, right? And this structure will use partial product generation and CSA, right? Carry save adder structures. So this is the example of a 4x4 multiplication, 4x4 bits multiplication, right? So the maximum propagation delay will happen this dotted blue line. So input comes in and goes through this logic and then finally go through the carry propagation, right? So this is the longest critical path, right, that determines the speed of the multiplier in this array structure. We can move that to this kind of a diamond shape into rectangular shape. So rearrange the connection, right? Then we can make it like a more the compact design to fit the rectangular floor plan, right? So typically array multiplier requires n partial products. If you can somehow reduce the number of a partial product, we can perform the multiplication faster, right? So there is for partial product generation, we always look at the multiplicand. We have a multiplicand y and a multiplier x. Multiplier, each bits are looked at. So we monitor each multiplier bits, and from that we generate the partial product, right? One by one, right? What if we look at this multiplier 2 bits at each 2 bit at a time instead of 1 bit at a time? Then we can effectively reduce the number of partial products. By looking at the multiplier bits and generate the partial product, then we can generate the fewer number of partial product. For example, by looking at by 2 bits, so 2 bits is just a 0. The combination of the 2 bit is that will result in 0, 1, and 2 and 3. So we pre-compute the 0, 1, 2, 3 cases for y, right? Then generate it like this. Then it can be easier, or we can reduce the number of partial product. But the problem is that for 0 and y and 2y generation, it's easy because the 0 is obviously easy and the y is easy, and 2y is just we can shift y to the left by 1. But for 3y generation, we need 2y plus 1y that requires addition. That becomes very bad. So how we can easily generate the 3y? Three-way generation, easier way is 4y minus y. That will reduce we can easily generate this kind of a 4y, because this can be generated by shift to left by 2 bits, and y is just multiplicand by itself. But this requires additional minus operation. But this kind of a thing can be simplified in the following: some boost encoding algorithm. We don't need to actually calculate this kind of a minus operation by clever encoding structures. Boost encoding, we use some encoding to eliminate the 3y generation. So instead of generating 3y, we generate the minus y, then add that 4y in the next partial product generation. For example, in this table, for 0, 0, we want 0 generation, 0, 0, 0 generation, y, and 2y, and 2y, and this is the 3y, and 3y. But depending on the previous group, MSB of the previous group, right? Because x2i minus 1 is the previous group. For example, if we have x0 and x1 and x2 and x3 x4, etc., we look at group it like a 3-bit and overlapping by 1 bit. We each group each one like that. So the initial first 2 bits together with the 0, artificial 0 at the below the binary point. So we look at this 3-bit first, and then depending on the lower bit, in this case the obviously 0, but in this group, for example, the previous group of the MSB is the 1, then that directly corresponds to the y. This is the 4y generation, similar to 4y generation. So, and that generation is considered to be the y in this next group generation, because this is all 2-bit shifted, right? So in this case, if the MSB is, each group of the MSB is the 1, then we minus 4y. So this is the 2y plus 2y. We transform that minus 2y plus 2y, or 4y. This is minus y plus 4y, with minus y plus 4y, like in this format. So this one supposed to be 0, but in the previous group is 1, so y is coming in, so y plus y, right? In this case, the y must be generated, and previous group there's no carryover here, so 0 is added, so y generation. For here it's supposed to be y, but previous group will add the carry out, so that should be the 2y. In this case, we only generate minus 2y. In this case, minus 2y, but y is going in added up in this group, so that becomes minus y. In this case, 3y is supposed to be 3y. Instead of 3y, we put the minus y. Right? In this case, minus y, but in the previous group, we have a y coming in. So 0, like this. So this kind of encoding use the purpose of this boost encoding to generate each two group, generate the easier partial product generation, but by referring to MSB of the previous the group, we can simplify the generation of the partial product by having the shift operation or the sign inversion. We'll go through each one by one again. Here, just y. Here, y, and coming in y, so 2y. Here, it's supposed to be 2y, but 2y instead, since MSB in this group is 1, we allow 4y generation here. So that becomes what happens? This is so minus 2y, right? So 4y is moved to the next group as y in that group, right? So this one is minus y, because here it's supposed to be minus 2y plus 4y, and we have addition coming in y here. So this one and that one and added it up, so it becomes 4y. Minus y, and 4y will move to the next group, and they become the y, right, in the next group. So here is supposed to be 3y, so minus y plus 4. Let's go to the next slide. Here that's supposed to be minus plus 3y, but that decomposed into minus y plus 4y, right? So minus y here encoded. The final here supposed to be 3y generation by looking at 2, but that comes to minus y plus 4y. One is coming in, so plus y. So this adding up correspond to 0, like this. Here, minus 0, minus 1, minus 1, minus 2, and plus 2, something like that. Okay. For boost encoder, we take the 3 bits and generate the x and 2x and minus sign. Depending on these 3 bits, we generate the partial product by decoding this x and 2x and mi. If the x is selected, then the y directly go through, and 2xi is selected, then the bit is shifted in, right, to the by left, and to implement the 2 times y here. For the m is asserted, we invert that all the partial product generated value to get the inversion. This is a visualization of partial product generation using dot notation. As you can see, the boost algorithm generates the positive and negative partial products. So we have to represent the number in 2's complement. So the MSB will be the sign, right? This will be the sign. The sign need to be extended to add them all, right? So in the partial product generation, for minus sign generation, we just invert it. But for 2's complement, we have to add 1 at the LSB to constitute a minus value. So we take the sign to LSB and then to generate the 2's complement properly, right? So this is all kind of all partial product that we have to add them up. But as you can see, there's some hardware portion that they're repeated and not efficient. So we can simplify the sign generation and addition of those by having the following operation. For example, if you invert the sign and add that all 1, then it is the same as the sign extension. This is the same, right? All partial generation, we invert the sign at the MSB and then add 1. Because of this all 1, for example, if the sign is 1, then S bar is 0, right? 0 and 1, 1, 1, 1, 1 is the same as sign extension, right? If the S is 0, then this is 1, and if 1, 1, 1 plus 1 become all 0. So it's the same as the sign extension. So sign extension can be simplified by this simple logic operation. But here is a constant 1 here. We can pre-calculate this 1 value because those are not varying, right? If you pre-compute, then we have a remainder of the 1 shown in here. So 1, 1, 1, 1, 1, 1. We just add those things. That's the final answer. So overall addition, number of bit for addition is reduced compared to the previous sign extension. So far, we just looked at the unsigned number multiplication, but for the signed multiplication of the two number will be a little different. We have to take into account more cases. So sometimes the higher radix boost encoding is used rather than radix 2 so far. And array versus tree CSA networks are also present. So all these kind of complicated things we are not gonna cover in this lecture. So if you're interested in, you can find it in the text. Google it and find the paper and look it over. Okay.